we want to find out this limit. I'm going to use this lemma I proved in a previous video. So this limit kind of reminds me of the definite integral from 0 to 1 of the integrand. What's the integrand? The floor of 2 over x minus twice of the floor of 1 over x dx. The reason is because so it's a 1 over n times a infinite sum. So it's just like we over the interval from 0 to 1 divide it into n equal parts. Right? Partition, even partition, a special case of Riemann sum, where the length of each interval is just 1 over n, and we evaluate the function at each little interval at the right edge of the small interval. Right? So the first functional value at the first small interval should be f of 1 over n, and the functional value at the we select at the second interval should be f of 2 over n, and the f of 3 over n in the third interval, and so on. So k from 1 all the way up to n, right? 1, 2, 3 all the way up to n. So here we have twice of n over k, right? That's the reciprocal of k over n. So that's why we have 2 over x and 1 over x here. And still, we don't know if this improper integral converges or not, right? Improper integral because we have a problematic point where x equal to 0, then it's unbounded. But first of all, let's put a question mark on it. Then let's use a substitution. Let's let 1 over x equal to t. Then x is equal to 1 over t. Then dx is equal to minus 1 over t squared dt. Then my integral should equal to also remember change the boundaries, right? When x is equal to 0, t is equal to positive infinity. When x is equal to 1, t is equal to 1. Right, the integrand should equal now to minus dt. Here we have a minus sign out here, right? So dx becomes this. So we have a t squared at the bottom, dt at the end. Inside we have the floor function of 2 over x. That's 2 times t, right? Floor of 2 times t minus twice of the floor of t. All right, still we have a question mark. Because again, this is an improper integral, right? We don't know if it converges or not. But first of all, let me just get rid of the negative sign and switch the boundaries, right? So from 1 to positive infinity. And because we don't know if it converges or not, let me just be more rigorous. Let's just call I equal to limit of n approaches infinity of integral from 1 up to n integral t squared floor of 2t minus twice of floor of t dt. Okay. Now let's split it into, let's just call this integral as I sub n. I sub n is equal to integral from 1 up to n floor of 2t over t squared dt minus twice of 1 over n floor of t over t squared dt. Okay, now let's just call this first integral as I1 and second integral as I2. All right, if they both exist, then we're good. Then we can let n approaches infinity and see if the limit exists. But first of all, for I1, let me just use a u substitution just to get rid of the 2 in here. And so that it'll look more similar to this integrand. And hopefully we can just cancel out some terms. All right, so for I1, I just let 2t equal to u. Right? 2t equal to u. Of course, t is equal to half of u. Then dt is easily half of du. Then also change the boundaries, right? So I1 is equal to the integral from when t is equal to 1, u is equal to 2. T is equal to n, u is equal to 2n. So it's from 2 up to 2n, right? The integrand is now the floor of u, then over t squared, that's over u squared over 4 times dt half 1/4. Simplify everything, we have twice of the floor of u over u squared du. Right, that's after we simplified everything. So I1 is good. How about I2? I2. Now notice here that now my integrand is exactly the same as I2, right? So hopefully we can just cancel out something. Except we have to re-index it a little bit, right? Because we have different boundaries. Now let me just see if I can re-index I1 into I1 into twice of the integral from 2 up to n plus the integral from n to 2n. Right? Here I just write it without writing the integrand, right? Just so we keep in mind, right? That's our integrand. So twice of that. So this is good. This is good. So I2 can be written as in the end we have to multiply I2 by -2. Don't forget that. Right, so from 1 to n can be split up into the integral from 1 up to 2 plus integral from 2 up to n. Right. Later we will multiply that by -2. And here we have a integral 2 to n, 2 to n. Right. Hopefully this term will just cancel out later. Now my I sub n is equal to I1 minus twice of I2, right? I1 is this. So twice of integral from 2 to n plus integral from n to 2n bracket minus twice of I2. Twice the bracket of integral from 1 to 2 plus the integral from 2 to n. And my I sub n is now equal to twice of integral from 2 to n. Here I have -2 of integral from 2 to n, so they can just cancel out. And I'm left with twice of integral from n to 2n minus twice of the integral from 1 to 2. Right, that's what I'm left with. So this part should be easy to figure out, right? Just remember the integrand is this one, right? So let me just clear up the board. So we've just established the, we want to find out I sub n is equal to this, these integrals, right? The integrand is this one. So later we will let n approaches infinity. If the limit exists, then we're good, we're done. But first of all, that's the reason I didn't straight up use positive infinity. Instead, I use n, the later let n approaches infinity. The reason is because here I have n all the way up to 2n, otherwise I would have just maybe 1 all the way up to twice of positive infinity, something like that. But we don't even know if positive infinity and twice of positive infinity are same or different, depending on different contexts. But first of all, let me just find out, let me just re-index, right? Split up the integral into several integrals, right? So integral from n to n plus 1, and from n plus 1 to n plus 2, all the way up to 2n minus 1 to 2n. Right? In fact, we can write it as a sigma, as a sum, just to save some space. Right? So I sub n is equal to twice of the sum of integrals, right? Sum from where to where? From what? From k from, let me see, from n all the way up to 2n minus 1. 2n minus 1, right? The reason is because now I can have the integral from k all the way up to k plus 1, right? So for example, first is when k is equal to n, it's integral from n to n plus 1. Next one is k equal to n plus 1, so from n plus 1 to n plus 2. The last one is when k equals 2n minus 1. That's the integral from 2n minus 1 all the way up to 2n, right? Same thing. So let's don't forget the integrand. What's the integrand? There, right? The integrand, but here it's abundantly clear that if we have this interval, right, from k up to k plus 1, this small interval, right, very small, whose length is just 1. Now it's easy for us to see the floor, the value of the floor, right? What's the floor here? Floor is just k, right, because it's from k all the way up to k plus 1. Floor is k, so floor of t becomes k. And down there has t squared. T squared still remains t squared, right? Don't have to worry about that. So dt, right? Now we no longer have to deal with floor or anything, you know, very, very annoying. So now we're good. And don't forget we have to minus twice of integral from 1 to 2 integrand t floor, floor of t. What's the floor here? From 1 up to 2, floor is easily just 1, right? Just 1 over t squared dt. Right, now it's easy, right? So this part should be easy to figure out, right? So let me just find out, right? This one, this entire derivative is easily just minus 1 over t, and lower bound 1, upper bound 2. So that is easily just half, right? Half. So minus half, minus 1, yeah, half. So this part becomes negative 2 times half, becomes a negative 1, right? This part becomes a negative 1. And this part should also be easy to figure out, right? Because we can just, before we do the sum, we will just treat k as a constant and take out the k from out of the integral, right? And figure out the 1 over t squared. Entire derivative should be easy to figure out. I sub n is equal to twice of sigma k from n to 2n minus 1. Integral of, so take out the k, right? So k times the integral from k up to k plus 1 of 1 over t squared dt. So the antiderivative of 1 over t squared, like I figured out, is a minus 1 over t, right? Minus 1 over t, antiderivative. This time I'm going to use the lower bound of k, upper bound of k plus 1, right? K plus 1. So this time, what is it? So it's 1 over k minus 1 over k plus 1, right? And that is easily, let's just work out the, k times k plus 1, right? K plus 1 minus k, 1, right? So let's just copy it down that. So 1 over k times k plus 1. All right, that's my result of my definite integral, right? And here, then we just do the summation, right? But here I can just cancel out the k's, right? K and k cancel out. Now let's do the summation, right? K from n all the way up to 2n minus 1. And let's just figure this one. It's half. This integral is half, right? Minus 2. So that's minus 1, right? This. Don't forget that minus 1. And of course, minus 1 is not included in the sum, right? Just keep in mind. I sub n is now equal to twice of this. What is that? Twice of bracket k from n all the way up to 2n minus 1, right? First term is what? It's 1 over n plus 1, right? So 1 over n plus 1. Second term is what? When n equals n plus 1, right? 1 over n plus 2. All the way up to 1 over last term is when k is equal to 2n minus 1, right? 2n minus 1 plus 1. That's 2n quantity. And we have a minus 1 here. Then let's just quickly figure out this infinite sum, right? So when n approaches infinity, we will let n approaches infinity, right? So what's this limit as n approaches infinity? First of all, I know that this limit equal to gamma as n approaches infinity, right? As proven in the previous video. And also I know that I know that 1 plus half plus all the way up to 1 over n plus 1 over n plus 1 all the way up to 1 over 2n minus log of 2n plus 1 should also approach gamma, Euler constant, right? So here I just replace n with 2n, right? Exactly the same result, right? As n approaches infinity, so 2n approaches infinity, the same thing. Still approaches gamma, right? So I'm using this relation and that lemma, and to take their difference, because they both approach gamma. So after taking their difference, I have some quantity that approaches 0, right? Gamma minus gamma, 0. Cancel out. So that essentially means, so I'm using this equation minus that equation. So I can just simply cancel out 1 plus half plus all the way up to 1 over n, right? Because I have the same quantity here. So they just cancel out. I'm left with just 1 over n plus 1 plus 1 over n plus 2 plus all the way up to 1 over 2n. And I still have minus of logarithm of 2n plus 1, and I also have to minus plus log of n plus 1, right? So I still have log of n plus 1 minus log of 2n plus 1. that easily approaches 0 as n approaches infinity, right? So I could now just combine logarithm using the logarithm rule, right? Difference becomes logarithm of their quotient, right? Ratio, right? So that easily becomes logarithm of n plus 1 over 2n plus 1, right? I'll just get rid of that. Right, so logarithm of n plus 1 over 2n plus 1. Right, that's my logarithm. And as n approaches infinity, this part easily approaches half, right? Because if we divide everything by n, right, so 1 plus 1 over n at the top, bottom we have 2 plus 1 over n. So 1 over n, 1 over n. As n approaches infinity, they approach 0. So essentially it's just 1 over 2, right? Half, right? So this approaches log half. Log of half. And this infinite sum plus logarithm half approaches 0 as n approaches infinity. So there's only one possibility. So that is this infinite sum as n approaches infinity approaches the negative of logarithm of half, right? That's the only explanation. So that means this quantity approaches negative of logarithm of half. That is logarithm of half to the power of negative 1. That is log of 2, right? Log of 2. And now I can state that inside, right, this quantity approaches log 2, right? Log 2. So twice log 2 minus 1, right? So this whole quantity approaches twice of log of 2 minus 1 as n approaches infinity. I've really worked out, shown that the limit really exists. So I remember at the beginning I rewrote the limit into a definite integral from 0 up to 1 and then changed that improper integral into another improper integral from some constant as the lower bound all the way up to the upper bound being an infinitely large, right? Then upper bound I use n, then becomes 2n or whatever. Then I let n approaches infinity. Then the limit really exists, right? That is my limit of my original question. That is this result, right? But if we want to maybe, further simplify that or whatever, so that becomes logarithm of 4, right? Logarithm of 4 minus 1 becomes, so that minus log of e, right? So maybe a logarithm of 4 over e, right? But doesn't matter. So my final result